Hi, I'm Deanna Schreiber-Gregory, and I'm here with Walter Stroop. We will be watching a pre-recorded session on Bayesian analysis of GLMMs using PROC BGLIMM. Once the recording completes, Dr. Stroop will be answering questions that you submit in the chat window. So let's get started.
Okay, good morning, everybody. Welcome to this tutorial on Bayesian analysis of GLMMs. I'm Walt Stroop. I'm an emeritus professor of statistics at the University of Nebraska. I've been a SAS user since 1976. I worked with Russ Wolfinger in the early days of PROC Mixed and with Oliver Schabenberger in the early days of PROC GLIMMIX. Together we authored the SAS for Mixed Models series, and I've also written a book on generalized linear mixed models. Today we're going to be talking about the Bayesian analysis of GLMMs using PROC BGLIMM, which is a new piece of software from the SAS system. So by way of kind of a roadmap of what we're going to be doing today, I'll spend a little bit of time talking about GLMM basics. What are the defining elements of a GLMM? Give you an overview of the difference between Bayesian estimation and inference and the frequentist approaches that PROC Mixed and PROC GLIMMIX used. And then we'll get into three examples. The first example, all of the examples are from the SAS for Mixed Models book, the 2018 edition. First example will be a multi-clinic binomial data set that's in chapter 11. And what we'll do here is go through a preliminary BGLIMM run with all the defaults. And then we'll go through a set of diagnostics to see what works and what didn't. There's some necessary options to finally get a usable analysis. So at that point, we'll look at what we need to do to revise the BGLIMM run so that we do get a usable analysis. And then we'll walk through interpretation and some needed post-processing steps that are basically equivalent to the iLink option in PROC GLIMMIX. The second example will be a multi-level experiment with count data. This is in chapter 13 of SAS for Mixed Models. And then we'll conclude with a repeated measures example that was in chapter 8 of SAS for Mixed Models. So without further ado, let's get started. Here's a kind of a setting for generalized linear mixed models. So we need to pay attention to the distribution of response variables and the kind of model effects that we want to include. So the classical statistical model format is to equate the response to a systematic component and a random or residual component of the model. So classically, what we would do would be either categorical or continuous explanatory components of the model. So categorical would be simply an intercept plus treatment effects. Continuous, the simplest example of this would be a linear regression model. On the random side, we have random model effects, but we also have residual error structures, and these really come into play when we have serial correlation, as we will in the repeated measures example, or spatial. So the classical mixed model does normality for the responsible. And if we do that, then we would model the residual structure on what we call the R side. But we know that we also have response variables that are not normally distributed. We have discrete proportions with either two categories giving us a binomial distribution, or more than two categories for multinomial. We have continuous proportions that are typically modeled with a beta distribution. We have counts, either Poisson, negative binomial. We have time to event, and we could go on and on and on. So this is the generalized linear mixed model setting. And the attempt with GLMMs is to be able to cover as much of this as possible. So let's see how we do that. The defining elements of a generalized linear model, we have a linear predictor, which consists of a fixed effects portion. That's the X beta part. And that would include either the categorical treatment effect or the linear regression motif that we talked about in the previous slide. The ZB would be the random model effects, and we would equate this to some strategically chosen function of the mean, and that's called the link function. The random effects in a GLMM are assumed to be normally distributed with some covariance structure, and we'll talk about that as we work through the examples. The conditional distribution of the observations given the random effects is assumed to have some distribution, typically from the exponential family, and we'll denote its mean as mu and its covariance structure by sigma. Sigma is broken down into a component that's called the variance function and a component that's called the scale matrix. And the scale matrix can be something as simple as an identity matrix, or it can be a full-blown repeated measures covariance structure. The log likelihood in its scalar form is proportional to a member of the exponential family. So what you see here is the form that Nelder gave in his original work on generalized linear models. If you take this b of theta function and take its first derivative, that equals the mean of the distribution of the observations given the random effects. The second derivative gives you the variance function. And so the variance of this is equal to a scale parameter times that variance function. And so we'll talk about these as we work through the various examples. Theta is a canonical parameter, and the important thing to know about it is that it is a function of the mean, and this linear predictor through this G inverse is the inverse link function, and that relates the canonical parameter to the linear predictor. Okay, so if we go talk about PROC mixed and PROC GLIMMIX, this is what we call the frequentist approach to estimation and inference. And it is all likelihood based. We have a log likelihood, the log of f of y and beta. F of y and beta is obtained, so this is the marginal distribution. It's obtained by taking the joint distribution. So that would be y given beta multiplied by f of beta, or f of b rather, the random effect. We integrate out the random effects, and that gives us the marginal distribution, and this is the basis of obtaining maximum likelihood estimates of the model effects. This log likelihood is generally intractable, so there are a couple of strategies for dealing with it. The default algorithm in PROC GLIMMIX is linearization, or what's called pseudo-likelihood, or we could do integral approximation either with quadrature or Laplace. And so quadrature is available both in GLIMMIX and in PROC NL mixed. So what we do then is either through one of these computational strategies, we obtain estimates and standard errors. Pseudo-likelihood allows us to obtain residual maximum likelihood, or what are called RIML covariance estimates. These are generally preferred because they're essentially unbiased. Then we use estimates and standard errors to get either test statistics or confidence intervals. If we're working in a Bayesian, the gold standard here is to obtain a posterior distribution. So to get this, we have the same likelihood that we had from the GLMM distributions. But in addition to this, we have prior distributions. That's the f of beta and theta term that you have. Or rather sigma. Sigma is a vector of the scale and covariance parameters that need to be estimated. And if you thought the GLMM distribution was intractable, this is really intractable. So what happens in Bayesian estimation is it's approximated by simulation. So there's some steps in here. The first step is to specify the GLMM, and that implicitly defines this f of y and b given beta and sigma. And we specify prior distributions, and these define the f of beta and sigma. Then there's a tuning step, a burn-in step, and finally sampling the posterior distribution. Once we have that, we can get its mean, we can get its median, we can get strategic quantiles that we need, and those become the basis for credible intervals. So in this tutorial, we're going to focus on working with these models and leave it for another day to actually go through the considerable math stat that's involved in these estimation steps. So with that said, a little discussion of why should we use Bayesian methods and just not be content with PROC GLIMMIX. And there are a couple of reasons for this. One of them is that there are an increasing number of academic journals that prefer Bayesian credible intervals to classical significance tests. Some of these journals are actually requiring a Bayesian analysis, or at least they're forbidding the classical significance tests. More generally applicable reasons, however, are frequentist maximum likelihood estimates that we would get from GLMMix and Bayesian estimates with non-informative priors are essentially equivalent. And what this means is that when we're working with PROC GLIMMIX, we're implicitly assuming ignorance until the data are analyzed. And arguably, this compromises efficiency and accuracy. The reality is that studies don't begin in complete ignorance. If they did, we probably shouldn't be doing them. In many cases, there's a series of steps that we work through, certainly in the development of pharmaceutical products. And so a given study has been preceded by a lot of preliminary studies or at least similar studies. And so we know enough to specify moderately informative priors that allow us to use what we know. So that's some reasoning for why we should be working with Bayesian methods. So with that said, let's turn to our examples. First example was in Chapter 11, Section 5 of SAS for Mixed Models. It originally appeared in Biometrics in 1985. It was one of the earliest generalized linear mixed models to appear. This is an article by Beitler and Landis. The example has 8 clinics assumed to be a representative sample of a target population. There are 2 treatments, a control and an experimental drug. There are 2 groups at each clinic. There are a total of N sub ij subjects at the ith treatment in the jth clinic. These subjects are assigned to the ith treatment at the jth clinic. The response variable is the number of patients out of these N sub ij who have a favorable outcome. Okay, so the first step in coming up with a generalized linear mixed model that's appropriate for an experiment like this is there's a kind of a 3-step process that dates back to some work that Fisher and Yates did in the 1930s. So what you do is you specify what's called a treatment design and what they call the topographical design. It's also been referred to as the experiment design or the study design. I'll be referring to it as the experiment design in this tutorial, but it's the study design as kind of broadly understood. So this is an example of a blocked design. In this case, it's a multi-clinic design, but the same format would be applicable to match pairs, before and after on the same subject, field plot experiments, etc., etc. So here we specify the treatment design. It's pretty simple. We have 2 treatments. The experiment design, we have clinics and we have groups within clinics. So the full design would just involve randomly assigning treatments to the various groups, and each group would have these N sub ij patients, and we would go from there. So at this point, we could repurpose the analysis of variance table by listing sources of variation. And the way I like to do this is to begin by separately listing the experiment design and the treatment design, and list those sources of variation. So we have clinics, we have groups within clinics, and then I put strategically the treatment in its column in a row immediately above the unit to which the treatments are assigned. So here treatments are assigned to groups, and we end up with a combined sources of variation, clinic, treatment, and then what I call group within clinic after accounting for treatment. So once you have that combined, then you begin to think about what kind of variability is associated with each one of these sources. So clinics are a sample from a target population. So they have a probability distribution, and in GLMM, we would assume that their IID normal and their variance component we're denoting as sigma sub c squared. We have a linear predictor that has to account for the treatment effect, which is fixed, and the clinic effect, but we also have variability at the group level, or what I call the unit of observation level, and that needs to be accounted for or we end up with overdispersion. So the final model, the canonical link for a binomial distribution is the logit, or the log of the probability divided by 1 minus the probability. The conditional distribution of the observations given the random effects is binomial with parameters id sub ij and pi sub ij. And then we can estimate pi sub ij by taking the inverse link, that's 1 over 1 plus minus the linear predictor. So that gives us the form of the GLMM that we'll be working with. I should say that there is an alternative way of modeling this. We're not going to talk about it here because doing so requires PROC MCMC, and we're going to reserve that for another time. But you could model this by saying clinics have the same IID normal distribution that we talked about earlier. But instead of having a clinic treatment effect in the linear predictor, you could model the probability as varying at the unit level according to a beta distribution and with a mean of mu sub ij. And that mu sub ij could be modeled by the inverse link of a linear predictor that involves the treatment effect and the clinic effect. This is called a beta binomial model, and I'm just putting it up here because this is a very common way that people have of working with these types of data sets. And it illustrates a point, and that is when you're working from the description of a study design to what I call a sensible model, the criteria that you have to keep track of is there a one-to-one correspondence between the sources of variation that you need to include in the model and the model parameters. So linear mixed model, this is easy. You have a clinic effect, a treatment effect, and a residual effect. With the logit normal model that we just went through a couple of slides ago, we have the clinic effect, the treatment effect, and a unit level term, which is the clinic treatment interaction. In a beta binomial, you'd have the clinic effect, the treatment effect, and the beta binomial scale parameter. So either of those have a one-to-one match. If you leave the clinic treatment effect out of the linear predictor, you have a model that I call the naive GLMM. And the problem with it is that overdispersion is very likely in a model like this because you're not accounting for variability at the group level. On the other hand, if you include the clinic treatment effect in a beta binomial model, then you've got a problem because you've confounded the scale parameter and the clinic treatment effect. And so that's a not sensible model because it's overspecified. So just some things to keep in mind when you're setting up a model. Now, let's turn to the BGLIMM statements that you need for this example. If we did this in PROC mixed, we would have clinic and treatment as class effects. Our model, the syntax for a binomial distribution is the number of favorable divided by the number of observations in a given group treatment combination. The fixed effects is treatment. The random effects are clinic and treatment by clinic. And so what you see on the left-hand side here is the syntax for specifying those random effects in PROC GLIMMIX. Then you would ask for least squares means, you'd ask for differences, you'd ask for the inverse link, you might ask for the odds ratio, and you might ask for confidence limits. The equivalent BGLIMM program uses exactly the same class, treatment, and random statement. The differences are in the PROC statement. In the PROC statement, there are some diagnostic things that we need to ask for. We want what are called trace, autocorrelation, and density plots. We want all the diagnostics so that we can look at. There's an outpost option that we'll talk about later. And you can ask for various quantiles of the statistics of the posterior distribution. And then there's something called a deviance information criterion, that's DIC, which has the same role with Bayesian analyses that the information criteria have with PROC GLIMMIX. There's no LS mean statement in PROC BGLIMM, so if you want the least squares means, you have to write out their estimate statements. And if you want the difference, this actually turns out to be the log odds ratio, you can ask for that. And then if you output those estimates, then you can work with them to translate them back to the data scale. So what you'll get here with these estimate statements is just the model scale estimates. We'll talk about that in shortly. Okay, when you run a GLMM program, there's some diagnostics that you need to take a look at before you start looking at the results of the analysis. Two important plots are the trace, or what are sometimes called caterpillar plots, and autocorrelation plots. There's also a Guecki diagnostic, which compares estimates from early and late iterations, and they must be, quote, acceptably similar. There's a Heidelberger-Welch diagnostics, and the important thing here is, does the sample size provide acceptable parameter estimate accuracy? There's something called a Raftery-Lewis set of diagnostics. And the main thing we'll be looking at here is something called the dependence factor. Close to 1 is ideal, and we'll look at some examples of when it's not good and what that looks like. And finally, there's an effective sample size. And what happens is that when you're doing this sampling of the posterior distribution, autocorrelation can be a problem. And if it's large enough, it limits the sampling algorithm efficiency. And so the number of samples taken, it doesn't necessarily translate to the effective number of samples after accounting for this autocorrelation. So let's take a look at the diagnostics that we get. When we ran this default run, what actually occurred, the trace plots looked like what you see on the left, and this is what you don't want to see. What you see is kind of erratic behavior in the trace plot. It kind of looks like something you might see during an earthquake if you look at the seismometer. And the autocorrelation plot, the autocorrelation, even at very high lags, never goes to 0. What you want to see is something on the right. This is what the diagnostic plots will look like when we put in some options that we're going to talk about in just a second. The ideal trace plot is often been referred to as a fuzzy caterpillar, so that this is what you want to see. And you notice those autocorrelations are high at the first 5 or 10 lags, but they very quickly go to 0. So the right-hand side is what you want to see. If we turn our attention to the diagnostics, you look some worrisome diagnostics. If you look at the Heidelberger-Welch, the columns you want to be looking at are test outcome, and what you don't want to see is any of them having failed. In the Raftery-Lewis diagnostics, the important column is the dependence factor. They look okay for the 2 random variance components, but they do not look okay for the intercept and the treatment effect. They should be close to 1. I'm loath to specify rules of thumb, but you definitely don't want to see dependence factors that are greater than 4. Some other diagnostics to look at, ideally the expected sample size, or the ESS, it's got to be in the thousands. So when you see numbers like 174 or 301, that's good, not good. And you should not see efficiencies that are down around 3 or 6%. The other symptom here is if you look at the posterior summaries, you notice that the mean estimate of what's called VC2, that's the estimate of the clinic treatment variance. In GLMMIX, that estimate was very low. I think it was around 0.02. 1.29 is just implausibly high. And this is just not a believable estimate. And so if you put that in the context of all the other diagnostics that are not good, this run would not be considered a usable or defendable analysis. Some other diagnostics that you ought to be looking at, BGLIMM, you can print out the starting values. They ought to be pretty close to the GLMM solution or the GLMMIX solutions. And the Goecki diagnostics here, they look okay. If you look down that probability of a greater absolute Z, you want to see high p-values. You don't want to see p-values down around 0.05 or 0.01. So it's okay in this run, but you always should check them. Okay, so what do we need to do? Well, problems occur when we have an inadequate number of burn-in iterations, when we have inadequate sampling of the posterior distribution, when we have inadequate thinning. So what typically happens when we're sampling the posterior distribution is instead of taking every iteration, we only take every 5th or 10th or even 25th iteration, and that's called thinning. So if we look under the model information, we see that the burn-in size on default is 500, the simulation size of the posterior distribution is 5,000, and the thinning 1 means we're not doing any thinning at all. We could also think about priors, and by default, BGLIMM is either using non-informative priors, so this constant for the intercept and the treatment effect, essentially that's a uniform distribution from negative to positive infinity. And the problem with that is that includes a lot of territory where we know the parameter is not. And so if the prior is too diffuse, that can cause problems. The default prior for covariance parameters is an inverse gamma with parameters of 2 for shape and scale. And we need to take a look at what this actually looks like compared to where we think the parameters really are. And because this is sort of an attempt to have a one-size-fits-all prior, and it may not be the right thing to do. So if we take a look at this default prior, here's what the inverse gamma looks like. If we go back to a GLMMIX run, we could kind of take these as indicators of what the most likely values of the variance components are. And what we see is that for the clinic variance of 2, that's kind of high in the range of this default prior. The clinic by treatment variance, on the other hand, is less than 0.1, and so it's way down at the other end of that distribution. So it could be we've been having problems with this prior because it's kind of in the no man's land between where these variance components really are. So Christensen, in his Bayesian textbook that was published in 2011, has a strategy for specifying a kind of use what you know prior. And what the authors suggest is that you specify the most likely value of the parameter and then think about extremes below and above which you don't believe the parameter's value, or the extremes above and below which the parameter values are considered implausible. So find a distribution where the mode is more or less equal to that most likely value and look at the extreme quantiles of that distribution and see how well they correspond to what you consider to be the upper and lower extremes. So a typical approach for doing this with variance is to use the precision, that's the inverse of the variance, 1 divided by the variance, and then use a gamma distribution to kind of do a trial and error search for what seems to be a reasonable prior. So here's a little code that I use to kind of hunt for this. If the GLMMix, I've used the GLMMix estimates. If you use pseudo likelihood, you actually get an estimate of 0.06. And for quadrature, you get an estimate of about 0.01. So that translates to precisions between about 17 and 100. So I kind of went in between there and specified a mode of 40. And then I did a search with different possible values of the shape parameter, solved for the mode. So this little formula here, B equals mode divided by A minus 1, relates the mode to the shape parameters, or the scale parameter. And then I plotted different PDFs and CDFs, and I did a little hunt for which of these distributions, where their upper and lower extreme quantiles were. And out of that search, I came up with a gamma distribution with a shape of 3 and a scale of 20, which translates to an inverse gamma with a shape of 3 and a scale of 0.05. And that distribution, you can see the mode of 40 is sort of at the lower left end, but there's plenty of room for lower estimates and a little bit of room for higher estimates of the precision. And over on the extreme right-hand side, that I show how that distribution translates to the actual variance scale. So here's a prior that seems to be a little bit more in line with what we know about where the clinic treatment variance is. We can do the same thing with the clinic variance, and a resulting program that makes use of the changes that we need to make. The new options here are in bold. So you'll notice that in the PROC statement, I've increased the number of burn-in. The default was 500, it's now 2,500. I've increased the thinning from 1 to 10, and I've increased the number of Markov chains to 100,000. The default was only 5,000. So I'm still getting the plots, I'm still getting all the diagnostics. The model statements are different only in that I've added some options. This init equals list allows me to specify starting values rather than letting BGLIMM choose them. So I'm just using the starting values from the PROC GLIMMIX run. And instead of using a constant prior, I have a normal distribution. Unfortunately, these are centered at 0, but I have a normal distribution with a variance of 9. So this allows the distribution to be fairly diffuse in the area where the fixed effects are likely to be, but it doesn't include all that territory out to minus infinity or positive infinity. The random statements, I've split them. So I have a separate random statement for the clinic effect and the clinic by treatment effect. And I've got the priors, and they have to be specified in terms of the inverse gamma distribution. And so I've got the priors for each of these variance components that's a result of that Christensen search that we just talked about. So here's the final program that I've run. Here's some suggested or selected diagnostics. So you'll see all the trace plots and the autocorrelation plots look like they ought to look. The effective sample sizes are now well into the thousands, and the efficiencies, it's only 29% for the intercept, but the effective sample size is certainly adequate, and the trace plots and interaction plots look okay. Raftery-Lewis, all the dependence factors are now less than 2. Most of them are quite close to 1. We look at the other diagnostics. Trust me, they're okay as well. So the estimated variance components now, 2.11 and 0.06. Those are the mean of the posterior summaries that you see here. So those look reasonable. The model effects, the intercept, in this particular situation is actually an estimate of the logit of the probability of the drug. The the tau of control is actually the difference on the log scale between these. So that's effectively an estimate of the log odds ratio. So if you look down at the results of the estimate statements, you see the correspondence between these variables. The HPD intervals are what are called highest posterior densities. And what these are the narrowest interval that contains 95% of the posterior distribution. So this is kind of an analog to a 95% confidence interval, and it's a standard tool that Bayesians use to decide whether the treatment effects are statistically significant or not, or the Bayesian kind of intellectual equivalent thereof. So you look at the odds ratio, if there's a significant treatment effect, it should not include 0, and you can see, in fact, it does not. So this would be taken as evidence of a significant drug effect. Now, all of these are on the log scale. So we need to get them on the data scale. And before we do that, there's the posterior summaries. This is another way of looking at instead of getting an HPD interval, we can just get percentiles. So if you wanted to, another way of getting a credible interval would be to use the 2.5 and 97.5. These are the 2.5 and 97.5 percentiles, and you could form a credible interval that way, which would be more like what you would do with a standard confidence interval with PROC GLIMMIX. Okay, now all of these are on the log scale, so we have to translate them. So to obtain data scale estimates, we need to do what the iLink function or option would have done in PROC GLIMMIX. So to do that, we want to get the probability of a favorable outcome for the control and for the drug. We want to get the actual odds ratio. And there are a couple of approaches for doing this. One is to use the information from this outpost option, and there's something called the SUMINT macro that you can use. On the other hand, you could use the ODS output and then do a follow-up data step. So output uses a posterior sample data set. ODS simply uses the summary statistics. So let's look at each one of these individually. The outpost, we output a data set called Cout. Then we can do a little bit of post-processing. If we want the probability of the control, what we do is we apply the logistic function to the control variable that we calculated with the estimate statement. For the probability of a drug, we do the same thing with the drug part of the estimate statement. If we want the probability of the difference between these two probabilities, we can just take the difference between those two functions. And then the odds ratio, we just take e to the log odds ratio, and that will give us the odds ratio. And then this SUMINT macro, what we do is we refer to the data set. So the data set we created with this data step is called data SC, short for data scale. And then we list the variables that we want HPD intervals and means and standard deviations for. And then the SUMINT will give this listing. So we see that the estimated probability or odds ratio is about 0.5. The probabilities are about 0.25 and 0.4 respectively. The difference between those probabilities is 0.15. And then we see the HPD intervals. So the second post-processing thing uses the ODS output. So this output a data set called Datascale, or rather model scale. So we create a set called Datascale. And what I've done is I've done a separate data set for what would be the least squares means, and another data set for the odds ratio. So if the label is either control or drug, then we calculate the probability applying the inverse link. So here, rather than using the logistic function, I've actually spelled out what that is. 1 over 1 plus e to the minus mean. And then we apply the same thing to the upper and lower HPD limits, and that gives us the upper and lower limits on the models, on the data scale. We can do the same thing with the odds ratio by applying the E to the mean. That'll give us the odds ratio. And then we can also do those upper and lower limits. And then we just do a PROC print for each of these. And at the right-hand side, you will see in blue the terms that you want to look at. So the upper one, those are the probabilities. The lower one, those are the odds ratios. They're not going to be quite the same as what you get with the sum-int function, because they're, as I pointed out a couple of slides ago, they're using slightly different information. But either one of these can be used in a final report. So that's the binomial example. So at this point, let's go on to our second example. This was in chapter 13 of SAS for Mixed Models. It's a Splitplot Experiment. So we have a total of 6 fields. Each field is divided into 2 halves, and a method is applied. This is an agricultural cultivation method, is applied to one of the 2 half fields. Each one of these half fields is further divided into 2 plots, and there's a different seed mix applied to either one of these. The variable is they're doing counts of some undesirable weeds that grew there, so that the data are counts. And so this is a setup of our experiment. Now, if we do the same repurposed analysis of variance, sources of variation in the experiment design are the field, and the half fields are what are called whole plots, and then the divisions of those whole plots that are called split plots, or I've just denoted these as SP here. The treatment design, we have methods, those are applied to the whole plots. We have mixes, those are applied to the split plots, and they take the method by mix combinations along with them. So the combined sources of variation that we need to account for, you see in the right-hand column. So if we then work with those, we can start thinking about what kinds of distributions go with them. The field effects I've denoted as B sub k, and those are random because these are a sample. These fields are a sample of a population. So they have a normal distribution with a variance of sigma b squared. The WIK is the whole plot effect. It also has a distribution. The mix, or method mix and method by mix, I've denoted by alpha, beta, and alpha, beta, respectively. And those are fixed effects. So the distribution of the observations conditional on the block, whole plot, and what I've called the unit level or the split plot. That's the unit of observation. As a Poisson distribution, and its rate parameter is lambda sub ijk multiplied by u sub ijk. So this is what's called a Poisson gamma process, and the assumption is that the rate parameter varies at the unit level according to a gamma distribution with a mean of 1. So its parameters are phi and 1 over phi respectively. So if you integrate out the unit level effect, you end up with a negative binomial distribution. So the actual GLMM to be fit here is a negative binomial GLMM. So we have a linear predictor that has the fixed effects of method mix and method by mix. We have the field effect, we have the whole plot effect, and together these define the negative binomial BGLIMM. For reasons that will become apparent as we work through this example, it's actually better to work from a Bayesian point of view with the cell means form of this model. So what we do is I've let eta sub ij replace the eta plus the mix and method and mix by method effects that were spelled out separately in the previous slide. Okay, so the BGLMM statements, what you would do here would be to first try to identify reasonable starting values and reasonable prior distributions. So I've skipped all the steps that we worked through with the binomial, and this is a kind of final result. So you can see the burn-in options, the Markov chain options, the thinning options. There's quite a bit of thinning that needs to go on here because it's a complex design, and the negative binomial is a kind of a demanding distribution to work with. In the model statement, you see the same starting value list that we saw with the Beitler-Landis example, but you also see a scale prior here. So what this is doing is specifying a prior distribution for the negative binomial scale parameter, that phi that we saw in the previous slide. It has to be specified in terms of a gamma distribution. So here are the shape and scale, or inverse, I-scale, inverse scale parameters that were identified in a search for a reasonable prior. Covariance, we went to use the same Christensen search that we talked about earlier. There are actually two random effects, the field effect and the field by method, or the whole plot effect here. And they're close enough together that this covariance, this inverse gamma that you see here, worked reasonably well for both of them. In the model statement, this MEMX is the it's a variable that I created that identifies the 4 method by mix combinations. So you can get their LS means with an estimate statement. We just work through those 4 combinations. And then we have the interaction effect that you see here. It's kind of the standard contrast that you would use for an interaction in a 2x2 factorial design. We have the method main effect, and we have the mix main effect. So those are defined in the standard ways. And then we can output all those with an ODS output statement, and we also have an outpost option up in the BGLIMM PROC statement, and that outputs a data set called model scale. Okay, so if we look through the results here, the diagnostics, trust me, they're okay with this particular run. The BGLIMM results, again, are going to give everything on the link function scale, which in this case is the log. So these ME, MX, 1, 1, 1, 2, and so forth, these are the log mean, the means on the log scale, and their associated standard deviations and HPD intervals. And then you see also the results of the estimate statements. The first 4 are identical. The interaction, because it does not include, or it does include 0, that would be taken as evidence that there's no statistically significant method by mix interaction. So you can turn your focus at that point to the method main effects. So it looks like here there is a significant mix effect because its HPD interval does not include 0, but there's not a significant method effect. What we can then do is turn our attention to the I-links, the inverse links. So again, we could either do this with the outpost and some int macro. When we do that, what we see is these, if you take E to the method main effect and E to the mix main effect, that actually gives you an estimate of the ratio of the probabilities for these 2 differences. So you see that for mix, the ratio between the mix mean for mix 1 and for mix 2 is about 0.47, and its interval extends from 0.16 up to 0.86. Then you see that the mean estimates on the actual data scale, the rate parameter estimates for the 4 treatments are 18.4, 30.4, and so forth. So you can do that. That's the one approach to doing this. If you use the ODS output, you use the same strategy we saw earlier. I've got a set for the least squares means, where I take the inverse links for LSM 1, 1, 2, and so forth. And then I've got another data set called diff ratios. And I use, if the label is either method main effect or mix main effect, then I take E to those estimates, and that gives me the estimated ratios. So these are the two sets of statistics that you would calculate in this particular example. Our final example is repeated measures. This was in Chapter 8 of SAS for Mixed Models. The data originally were from an article by Littell, Pendergast, and Natarajan that appeared in 2000. We used it in SAS for linear models in 2002, and it's actually also in the BGLIMM documentation. There are three treatments here. These are actually asthma treatments. So the response variable called FEV1 is a measure of breathing comfort. There are two nasal treatments called A and C, and there's a placebo called treatment P. There was a baseline measurement that was taken that's called base FEV. And then once the treatment was applied to the subject, there were hourly measurements of the breathing comfort for about 8 hours. So none of the treatments lasted longer than that, but the idea is you take it's kind of like one of these nasal sprays. You take it, initially it's very effective, but it wears off over time, and they wanted to track how it wore off. There were 24 patients assigned to each one of the drugs. If we look at the repurposed analysis of variance, we have drugs. We have those are applied to each of the patients. So we have patient within drug. In repeated measures terminology, that term is called the between subjects variation. Then we have the hour effect, the drug by hour effect, and then we have the occasion within patient after accounting for drug. And in repeated measures lingo, that's called the within source of variation. The within sources of variation are assumed to be correlated, so we have to deal with that correlation structure. So the linear predictor is going to include alpha, that's the drug effect. The within subjects effect, I've denoted that as S sub ij. The tau is the time effect, or in this case, the hour effect, and we have hour by time. Now, one thing, just some preliminary plots here. The objective of this experiment is to see if the experimental drugs improved breathing comfort relative to the placebo, to actually see if there's any difference between the two experimental drugs. And the focus here is on how long does the improvement last. And so if you look at this, what you're seeing is a kind of in the placebo, nothing really happens. You've got a flat line around 2.8. In the other two, you get an initial increase and then kind of a straight line decrease over the 8 hours. So in order to address this in some way, shape, or form, your focus has to be on the drug by hour effect. So one of the things just to point out about the BGLIMM documentation, they refer to a model 2, which is a main effects only model, and a model 3, which has drug main effect, hour main effect, and the hour by drug interaction. And the documentation refers to this as a minor difference. It's not a minor difference. You cannot address the objectives of the experiment unless you include the interaction term in the model. So just thought I'd point that out. And I've actually made the developers aware of this. Okay, so alternative models. Well, the generic model, you have Y given the between subjects effect. The breathing comfort can be assumed to be normal with some mean and some covariance structure. This R refers to the covariance structure. It's actually block diagonal. You've got a total of 76 or 72 subjects here, 24 for each treatment. And within each one of those subjects, you have an 8x8 covariance matrix. And in this example, we'll do what we did in SAS for mixed models and use the AR1 structure. The between subjects effect is assumed to be normally distributed, and it has some variance component sigma sub s squared. So you can either work with this as an effects model where you have an intercept, that's my eta term here, The beta x sub ij term is a covariate for the baseline FEV1 term. Then we have alpha, the drug effect, tau, the time effect, alpha tau, the drug by hour interaction term, and we have the between subjects effect, S sub ij. The cell means version of this, we would just simply collapse the alpha tau and alpha tau term down into a cell means, or just have the alpha tau term in here. The other way you could do this is with an unequal slopes regression. Since most of the variability over time is a linear regression, instead of having alpha tau in the model, you could have alpha sub I and beta sub I times h. So h would be the hour, and so basically what you've got is a separate linear regression for each of the 3 drug treatments, and then you can compare the intercepts and the slopes. So here's the model. So take a deep breath. There's a lot going on here, but let's just work through this. We have PROC BGLIMM and sort of a usual set of options. In this case, the default burn-in and the default thinning was okay. We had to increase the Markov samples from 5,000 to 10,000. We've asked for all the diagnostics. We don't need an outpost option here because we're working with Gaussian data, so we don't need an inverse link step. The classes are drug, patient, and hour. The model includes the base FEV covariate and then the drug by hour effects. The random effect, we have the first random statement is the between subjects effect. The repeated statement, so this is kind of like the syntax that we have in PROC mixed. We have variation over hours within each patient by drug. The covariant structure is AR1, and this R and R core would allow us to print out what the covariance and the correlation matrices look like. The estimate statements here are comparing the drug by hour least squares means so the first one would compare A to the placebo at hour 1, and so the coefficients that you see here identify that particular difference. C versus P at hour 1, the coefficients here identify that particular difference. And then you can just do a copy and paste and adjust accordingly to go through hour 2, hour 3, and so forth. The other thing that you would want to do would get to get the least squares means for all the treatments at all the hours. So to do this, I kind of reframed the model statement. So here I've gone to the cell means form. We've got the baseline, and then we've got just drug by hour. And then what I did was I ran a GLMMix program to get the least squares means coefficients using the E option. And I simply used all those coefficients to define the least squares means. So unfortunately, it's a lot of bookkeeping, but if you take a deep breath and focus, it's doable. The other approach here is that you can use the linear regression. This is a lot simpler to do. So the difference here is we define a variable called h. So we do a data step and we define h is equal to hour. Then we have the same class statement here. The model statement's a little different. We still have the covariate, but now we have the drug, and those will be the intercepts for the linear regression. And h within drug is the linear slope for each one of the drugs. Then we can estimate the intercepts for each one of the drugs. That's just what we see in the first 3 estimate statements here. We can estimate each of their slopes. Those are the next 3 statements that you see: slope drug A, slope drug C. And then we can estimate differences between these, so we can see if there's a difference among the 3 drug treatments. And so the first set of those is intercept A versus C and so forth. And then we have slope A versus C. So if we look at the output for this, the first is the results for the effects model. We have all the least squares means. I've listed these by hour. You could do a PROC sort and list these by drug over the various hours if you wanted to. But here you can see what the mean breathing comfort is at hour 1 for each of the drugs. So you see it's up in the 3s for the A and C treatment, but it's only 2.8 for the placebo. And you can go through all the hours. The result on the right-hand side are the comparisons between these. And so these give the differences and their HPD intervals between the drug, each drug, and the placebo at each one of the hours. So you can see that for the first 3 hours, the HPD intervals have both drugs above the placebo, but by the time you get to the 4th hour, the A is beginning to show no difference between it and the placebo. And that pattern, there's a little blip at hour 5, but then at hour 6, hour 7, and hour 8, you see the same thing going on. So it looks like the C is actually the better treatment of these, looking at these simple effects. The other way to look at this is with the regression model. The left-hand side shows the raw estimates. On the right-hand side, we see the estimates that we're probably actually interested in. If you look at intercept drug A and slope drug A, that gives you the linear regression for drug A, 2.08 minus about 0.09 times hour. So that tells you that it's dropping over hours. If you look at the placebo, the intercept is only 2.4 or 1.4, and the intercept or the slope here is only 0.1. So that's telling you that for the placebo, it's essentially flat. And then you can see the differences that are estimated and the slopes that are estimated. And in that way, you can kind of see the differences between the various treatments looked at from a regression perspective. So if I was doing this, I would make use of the information from both the effects model and the regression model to get a complete picture of what happened here, kind of along the lines of how we use PROC GLIMMIX in SAS for mixed models. So that runs through the 3 examples that we've got. And just some final thoughts here then. So PROC BGLIMM sort of sits between PROC GLIMMIX and PROC MC, which is SAS's sort of more hardcore Bayesian procedure. BGLIMM can implement basically the same models as PROC GLIMMIX. When you run this, there are a lot more diagnostics that you have to pay attention to than you would if you were doing a GLIMMIX run. You need to look at the trace plots. You need to look at the expected sample or the effective sample sizes, the dependence factors, the other diagnostics that we talked about. Typically, the NBI, NMC, thin, and prior options will need attention. The defaults very often do not work, particularly when you're working with non-Gaussian data. You also need to, when you're working with non-Gaussian data, you need to use either the outpost or the ODS output approaches to do the kind of things that you would ordinarily do, that you would do with the iLink option if you were working with PROC GLIMMIX. So it's all doable. They're just a couple of extra steps that you have to work with. Now, the last thing is, a lot of people will ask, well, how does BGLIMM compare with PROC MC? And you could do all the models that we talked about here, plus the beta binomial model that we talked about earlier with PROC MC. MC offers a lot more flexible specification of prior distributions. And of particular note is that when we worked with the priors in the Beitler-Landis example, we could either do the constant or the normally distributed prior that was centered at 0. In PROC MCMC, you can center that prior at the fixed effect starting value, and often that's really a helpful thing to be able to do. PROC MCMC will allow you to fit nonlinear mixed models and semi-parametric models, or mixed models with smoothing splines. It also allows non-Gaussian random effects. So that shows up in the beta binomial model. There's also a Poisson gamma mix model. And those are things you can do with PROC MCMC. But the fact of the matter is, most of the mixed models that you would work with in PROC GLIMMIX are doable in BGLIMM. They allow you to make use of prior information. And if you're working with academic journals that prefer the Bayesian analysis to the more classical analyses, this gives you a way forward. So I hope you found this tutorial useful. If you have any questions, you can contact me. The most efficient way to do it is to send me an email. It may take me a couple of days to respond, but I will respond. And thank you very much, and hope you found this useful.
Thank you, Walt, for that presentation.
You're welcome.
So we were monitoring the chat and everything, and we saw that we have some pretty great experts that were able to answer some of the questions, but there were some questions that we'd like to ask that hopefully you'd be able to answer. One of them is, could you say more about how you came up with meaningful and defensible prior distributions?
Yeah. What I did in the, can everybody hear me okay? Can you hear me okay? Yeah. Okay. What I did in the tutorial was for simplicity, I used results from PROC GLIMMIX as starting values. In real life, what would happen would be that you would, if you're a data analyst, you're going to have a conversation with the subject matter scientist, and you might do a preliminary run in PROC GLIMMIX and get estimates, but then kind of think about values of the variances, for example, that you consider to be possible, and values that you consider to be absolutely implausible. And a lot of times the researcher, if you're working in a setting where there's like in pharmaceuticals, there are typically a series of trials that occur from the research and development to, through the whole process until you're ready to actually license the product. So the researchers will know something about the results of the previous studies, and you can use those as a way of understanding what the value of the parameter ought to be and what values are just, nonsense low or nonsense high, above or below these values, they're just not going to happen. And so then it's kind of an art science process. There's no magic, exact formula for doing this, but the procedure that Christensen described is a very good one, and that is, if you're working with a variance, convert it to a precision, and then do a little bit of trial and error with different values of the gamma distribution. And what I didn't really talk about here was, once you get a perspective value, put it into a BGLIMM run and see how the diagnostics come out. And if you're having trouble deciding between a couple of priors or maybe even a handful of them, try them all out and look at the diagnostics and see how they compare to one another. And the one that's producing diagnostics that are showing the least evidence of any difficulties, so if they have the best looking trace plots, the lowest autocorrelation, the best effective sample size, and so forth, then that's the analysis you want to go with. And then, at that point you go for it. So it's as much art as it is science, but I think an important thing that I really didn't talk about in the tutorial, but I think is really important, is make sure this is a dialogue between, if you're the statistician, make sure that you have an open dialogue with the subject matter scientist, and you're really, seeking out what they know and using that when you're doing the analysis.
So excellent. Thank you so much for that. One other question that we have is, could you describe that repurposed ANOVA process you were talking about? We've got about 5 minutes left, so I'm hoping you'd be able to do that.
Oh, okay. So the first thing you do is you think about what are the elements of the design that you have before you ever start applying any treatments. So if that last example that we had was a repeated measures. So you know that you've got the 24 subjects that you've got a total of 72 subjects. You know that you're going to divide them into groups, and they're going to be assigned to the different treatments. So you've got the subjects, and each subject is going to be measured a total of 8 times after the treatment's been applied. So the components of the design before you start applying treatments are subjects and then occasions within the subject. Then you know that you're going to randomly assign these 3 treatments to the subjects. So your treatment design is basically those 3 treatments. And then, once they get assigned to subjects, you're going to take multiple measurements, and you're going to want to monitor something about the change in the response that is occurring over time. So now you've got a design list and you've got a treatment list. So you put those together, and now you've got treatments, you've got the subjects within each treatment, you've got the times of measurement, you've got any effect that the treatment is having on those changes over time, and then you have the within subject variability. That's where you're actually taking the observations. So if in our example we had normally distributed data, so that would lead you to set up a covariance matrix, and you could really just go to chapter 8 in the SAS Mixed Models book and follow the example as it's laid out there. If you were dealing with non-normal data, then you'd have to do something like what we did with the Beitler-Landis data. That was our first example. And that is, you would actually have to take that unit level term and include it in the linear predictor. And that's where the covariance structure would be. So you'd have between subjects effects, and then you'd have within subjects effects. They'd both live in the linear predictor. And then the within subjects effects would have a correlation structure, which might be the same AR1 that you used in the model that we looked at in the third example. So that's, the basic idea is, what do you have for a design before you start applying treatments? What are the treatments? How do the treatments get applied to the design? And then what are the sources of variation that you end up with? And then once you have that list, then you begin to associate what kind of treatment model effects need to go with them in order to form the linear predictor. So that's a long answer. If any of that was unclear, you can shoot me an email and I can write it out. But I encourage you, there's actually a chapter in SAS for Mixed Models, chapter 5, where we go through in a lot of detail what this repurposed ANOVA process looks like. We kind of have a kind of a basic example and then about 8 variations on it. And if you read through that, that's probably the place to start to really understand how this process works.
Excellent. Thank you for that. And I've seen some other questions coming in, but I'm thinking they might require a bit more time. So for anyone
Okay.
else who has any more questions, I really encourage you to reach out to Walt and ask them, because
Yeah.
obviously he's very knowledgeable and would love to answer your questions.
Okay.
Um,
And if you send me an email, I'm kind of tied up tomorrow through next Tuesday, but I promise I'll respond to you by Wednesday or Thursday next week.
Excellent. Thank you so much for that. Your knowledge is very valuable to us as a community. Thank you, Dr.
Okay.
Stroop, for joining us
Thanks.
today and answering all of our questions on your presentation, Bayesian Analysis of GLMMs using PROC BGLIMM. So we hope you will continue to explore the other great content we have available at SAS Global Forum Users Group channel. And don't forget to take the session survey on the SAS Global Forum Attendee Hub. Thanks, everyone.
Okay. Thank you.